Let me begin this series of talks on algorithmic sustainable design, the future of architectural theory. So let me begin the first lecture, recursion in the Fibonacci sequence, universal scaling, and biophilia. The point to begin is to explain the title of the lecture series, Algorithmic Design. What is algorithmic design? An algorithm is a set of instructions that can be followed to achieve a desired result. The end result is not always predetermined. In mathematics, we have an algorithm for computing something that is predetermined. We go through a series of steps. It's an algorithm, and we compute what we want to compute. Systems that are predetermined are like finding a sine of 35 degrees, a standard result. But when you go to complex systems like architecture, there is no predetermined end result. You have an infinite number of different results, some of which have better qualities than others. So an algorithm, in that case, is not a way to a unique result, but an algorithm cuts down the choices, and each successive step of the algorithm gives you a state. So, for example, if you have an algorithm with several steps, after the first step, you cut down the choices from 1 million to, say, 100,000, and the next step, you cut the number of choices from 100,000 to 10,000, and so on. If your algorithm is good, then you are comprehending the complexity of the problem and are reaching toward a desired result. And there could be many desired results, but by many, as Christopher Alexander points out in The Nature of Order, by many, they can be infinite. But suppose for the purpose of comparison, you can have 10 good possible end results. So starting from 1 million to get down to 10, the algorithm is an efficient one, and otherwise you will not be able to cut through all the complexity. And the key to an algorithm is that it breaks up the problem into smaller steps, eliminating undesired complexity at each step. Some of these algorithms use recursive feedback. Recursive means you do something once, and then the result of your action then can feed into the next step, so that your algorithm has some feedback that helps you in the direction you want to go to achieve an optimal result. This is to be contrasted with the conception of all at once. All at once is a tradition in architecture. The great architect conceives everything finished in his or her mind, and then writes it down, and then it gets built. Well, even the simplest building is a problem of such extraordinary complexity that is not very viable. Now, I would like to suggest that we use algorithms to compute a result, and we use algorithms to design. So I'm making the comparison between design and the computation. The end the end result of a design, a successful design, can be compared to the end result of a computation. If we don't have an algorithm, what do? We retrieve a result from memory. If you're forced to solve a problem, a mathematics problem, and you have no idea of how to solve it, you have no algorithm to solve the problem, then you guess. Now, what is guessing? Guessing is using intuition. And what is intuition? Intuition relies strongly on memory. So memory in architecture is a memory of typologies that one has experienced and one has learned and inputted. So when you are faced with a problem, without realizing what you're doing, you are outputting memory. So your exposure to different typologies will influence your solution, and you mistakenly think that such a solution is totally innovative. It is not. What I'm suggesting, however, is that you can get out of memory dependence by using an algorithm. And hence you can become more creative. And of course, every architect wants to be more creative. Now, the other part of the title is sustainable design. My meaning of sustainable is slightly different from what is used today by many architects. Nature uses certain rules to create form, morphogenetic rules that of all the natural phenomena that we see around us, both animate and inanimate biological forms and physical forms. If we as human beings think of architecture as an extension of biology, because it is human beings, which are a biological phenomenon, creating structures to house themselves and their activities, then it makes sense for us to follow the morphogenetic rules that nature herself follows. So this is the broader meaning of sustainable design. In traditional and vernacular architectures, natural materials that are freely available have certain limitations, structural limitations, and they actually constrain the build form to certain geometries. With the Industrial Revolution and modernization, we have materials that are so strong and so powerful that we have no structural limitations at all anymore. So one constraint that kept the built environment to these sort of morphogenetic rules that were more natural has disappeared in the last century, and now we're free to build any shape we want. But the results, therefore, are free to be either adaptive to human sensibilities or totally violate human sensibilities, and there is no check. Many people today claim to make sustainable buildings by using technology like solar panels. Well, that's a step in the right direction, but a technological fix does not connect to the intrinsic geometry of nature, and philosophically one is really getting away from the concept of sustainability the way my friends and I understand it. Now, I'll begin the meat of the lecture with a recursion, an arithmetic recursion, a repeated operation with feedback. The Fibonacci sequence is well known to most architects. We start with the number 1, then we add the 1, and then we take the 2 previous numbers and add them to get the next number. So that way I generate the sequence 1, 1, 2, 3, 5, 8, 13, etc. And it's an infinite sequence. Continuing, I can keep generating any number in the sequence by adding the previous two numbers. There is a connection with the golden mean, which I will address later, but that does not concern us now. Well, after one page of work, I'm able now to present an important concept for architecture, the universal scaling hierarchy. In the Fibonacci sequence, we have a very nice tool. If we take the alternate terms of the Fibonacci sequence, we can use them as a check for subdivisions in an adaptive design. So I have taken every other term of the Fibonacci sequence that I showed earlier, and I get what is now also an infinite sequence with the numbers 1, 3, 8, 21, 55, 144. And I propose to use these as a check for subdivisions in an adaptive design. For example, here is the method. Going up in scale, I will take the smallest built scale, which is determined by physiological constraints, say a step that I know has to be a certain height because of the size of human beings. So I propose that the next largest scale in a design should be about 3 times that step. The next largest scale about 8 times that step. The next scale about 21 times that step. The next about 55 times. These are the numbers of the sequence that showed. And I go up until I get to the size of the whole building. Now, this is not meant to be a straitjacket, that everything has to be exact, but it's meant to say that if a designer has complete freedom in making an element of his or her building in size, then they can use the universal scaling that I proposed to help in the design, instead of wondering, should I make this 1 meter or 5 meters? Well, by checking the Fibonacci, the alternate terms of the Fibonacci sequence, that will give a hint as to what fits in the scaling, and that will make the building more harmonious. Now, it is our contention that it will make the building more harmonious, but we will discuss that a little later. The design should try to avoid significant scales in between these approximate scales. So we all know of design which is too busy. There are too many things happening at many different scales, and we would like to avoid this effect is undesirable. So let me now show a corollary application, starting from the largest built scale, say the size of the building itself or one of its main features, and going down in scale. I will use exactly the same numbers, and this time I will divide by those numbers to get the ratios. So the next smallest scale should be 1/3 of the largest dimension. The next smallest scale should be about 1/8 the largest dimension. The next should be about 1/21 of the largest dimensions, etc. And how far down do you go? Well, since the universal scaling rule is an infinite sequence, we can go right down to microscopic sizes. Do you need to have all those scales precisely? Absolutely not. But again, this is a check for the relative sizes of elements that one uses in a design. And even more important, going down in scale means that you go down to 1 meter, half a meter, 20 centimeters, 10 centimeters, 3 centimeters, 1 centimeter, half a centimeter. When is the last time that contemporary architects paid attention to elements on those sizes? These are the human scales. And I'm afraid that with a technological style of building, we have not paid much attention, or any attention at all, to these human scales. So by using universal scaling, I am weighting as far as showing that they're equally important. The small scales are in the same sequence as the large scales. So while we pay attention to the height of a room, the height of a ceiling, we don't pay attention to the 10 centimeter scale. What's on the 10 centimeter scale? Well, the room I'm speaking in, where's the room I'm speaking in? Yes, the room I'm speaking in has nothing on the 10 centimeter scale. If I were in a more traditional building, there would certainly be something, small detail, small trim, that while such elements have been ignored and not included in much contemporary architecture, we see now that from a mathematical point of view, they offer something to the design on many different scales. So here is the golden rectangle that everyone knows. It has a ratio of the golden ratio 1 to 1.618. And we are going to subdivide it in order to get a square out of it. So I subdivide it so that I get a square, and what is left on the right-hand side is another golden rectangle. it is smaller, of course, but it has a similar proportion, but it's standing up instead of lying down. In order to get a golden rectangle that's also lying down, I take one more cut and create a square. Square on top, and now I have two self-similar golden rectangles lying horizontally. I can continue this process indefinitely, and I get a whole bunch of golden rectangles standing up and another set of golden rectangles lying on their sides, getting smaller and smaller. So I'm not interested in the rectangles per se. What I want to do is generate these lengths that I show. There is a set of horizontal lengths that are shown on top of the rectangle and a set of vertical lengths that are shown on the right. Well, these lengths are important because of the relative ratios. The relative ratios of these lengths, both the horizontal and the vertical, are those numbers that I derived for you just a few slides ago. So this is how the numbers arise, and we can get a little better visual idea of the relative scales. Suppose we have a building, we want a subdivision, so we go to the next smaller length, we have that subdivision, and then the next smaller length will give us the subdivision of that building. Each of the subdivisions that I'm talking about is normally not a single thing. It is usually several subdivisions or tectonic elements at that particular length. So a little mathematics now to relate what I'm doing to what people know about the golden ratio. If you take the limit of the alternate terms of the Fibonacci sequence, as the terms get large, you get a fixed irrational number, which is 2.618. Now, one would say, why go through all this trouble of adding those numbers? Why don't we take powers of 2.618? Well, we cannot, because the Fibonacci sequence is not a geometric sequence. That means it is not a sequence where you have a number a to the nth power, because the way you get it is by adding the last two terms. Anyway, these are mathematical details that do not concern us. But for the practicing architect, I propose the exponential sequence. So everyone has a pocket calculator, and each pocket calculator has the logarithmic constant e, which is approximately 2.72. Now, if you take powers, integral powers of e, then you get numbers that are approximately those numbers that come from the universal scaling sequence, as you can see from by comparing them. So if you are on the construction lot and you have your pocket calculator, you can do these checks of the relative sizes by using E. And of course, this is I may be ostracized by my mathematician colleagues. This is very approximate, but since I'm talking about a constraint on design that is itself supposed to be approximate, it doesn't matter if these numbers are approximate or not. Now, when you get to the high powers, say e to the 10th, and you look at the corresponding term in the universal scaling sequence, well, there is some difference, but we don't worry about that. Some graduate students has to write a PhD thesis about which is more correct, but I'm not going to do that. Now, E has an special interest. We know that the Fibonacci sequence has a let's switch here. Yes, the Fibonacci sequence has a long history and application to the growth of sunflower seed spirals and the growth of leaves, etc. So what I'm talking about does have a direct relation to the way plants grow and natural forms, biomorphogenic processes. Little e also does, because little e determines the shape of animal shells, horns of mammals, and mollusks and all sorts of interesting things that are well of side interest to architects. But for this lecture, it serves just to point out that there is a connection with natural forms. Now, the universal scaling hierarchy extends the old rule of three used in the past. In many architectural rules of thumb, the master architect would say, well, if you want something on a bigger scale, you multiply by 3, or if you want to subdivide it, you divide it by 3. That's the old rule of 3. Well, what we have done is to give the other terms. And there's a certain pleasure in mathematics when you take a result that's been around for millennia, and you say, well, this is incomplete. There are, in fact, more terms than the number 3, and the other terms are the ones I have given you. So there's a certain intellectual satisfaction of this. So I give many more arguments in my book, A Theory of Architecture, chapters 2 and 3, and the person who really got into this is Christopher Alexander in The Nature of Order, especially in book 1. For those of you who don't know, my work is intimately related to Christopher Alexander's work because I helped him to edit The Nature of Order over 25 years. So what I write in my books, of course, I have learned from Christopher, and I hope to have made a few independent discoveries here and there, but our work should not be my work should not be taken to be independent of his. Here is the cover of Christopher's book. The Phenomenon of Life is volume 1. Is where he discusses the scaling and boundaries, essentially stuff that I'm covering in the first lecture. And here's the cover of my book that I gave a little more mathematical justification and discussion to help Christopher's arguments. So I promised that I'm going to relate this to the golden mean. If you remember that in the universal scaling sequence, the ratio of the terms tends to this number 2.618. Well, 2.618 happens to be the square of the golden mean phi. Golden mean, of course, is 1.618, and you have phi squared equals phi plus 1. That's how we get 2.618. So this is an interesting coincidence, but I want to emphasize that this has nothing to do with the proportions of rectangles. The most popular golden rectangle is the credit card. Well, that has nothing to do with universal scaling. It's just a rectangle. Many people are amazed at the application of the golden mean to the Parthenon, but I'm not, because when you draw the golden mean in front of the Parthenon, you also include the triangular pediment. It's not the triangle that's obvious that is a golden mean. You have to draw something in space. Anyway, traditional applications of the golden mean are to rectangles. And here I'm not talking anything about rectangles. I'm talking about ratios between dimensions in the same direction. Now we come to the focal point of this lecture. Which architectures obey universal scaling? Well, it turns out that all traditional architectures obey universal scaling to some form. Gothic architecture, classical Western architecture, the Greco-Roman tradition, Islamic architecture in its many manifestations throughout the world, vernacular architectures used all over the world, and traditional architectures from all cultures and all periods. There are two exceptions. One is international modernism, and the exception, I think, can be traced to what I mentioned earlier, this tremendous freedom from material constraints that we obtain with very hard and durable materials. And the other one, the other exception goes throughout all of history. That is defensive military architecture that is meant to keep people out. So there is no need to have subdivisions. You want to have a hostile appearance. So that does not obey universal scaling. Here are just a few examples. This is the Masjid-e-Shah, Isfahan, the great entrance, and we can see that the the main arch has a ratio to the secondary arches on either side, which is approximately what we propose at 2.7. Well, this is about 2.5. The width of the main arch compared to the width of its boundary. That's an important point that I will discuss later. The boundary of something. Another example from Islamic architecture, a window from the Alhambra in Granada, Spain. The width of the entire window compared to the width of the subsidiary window is not exactly half. It's closer to 2.75, which is the number we want. So this is the actual space. And why does this occur? Well, because there is extra material here, and we can continue actually to measure these pieces and come up with interesting relationships and more terms of the universal scaling sequence. My friends who are architects told me that at this stage I should just abandon, in this particular talk, I should abandon talking about numbers and text and just show pictures where universal scaling is found. But I have decided for aesthetic reasons just to show sketches that I make myself. So I really don't want to make hundreds of different sketches by hand in order to illustrate these lectures. And anyway, I will have to go and either visit places myself with a tape measure, or find sufficiently sharp photos from a good perspective in order to do these measurements. And I have other things to do. Well, I have to prepare the rest of the lectures of this series. So I'm not the one to do the measurements. However, let me see. Yes, I call forth on interested students to look at traditional architectures of all different cultures and all different periods, and to do some measurements and see if they find the universal scaling and to what degree they find it, or if they don't find it. And that should be an interesting set of exercises, because I'm giving out a challenge, and the challenge is the following: it's not that a few select buildings obey universal scaling. The challenge is the following: is that most, if not all, buildings of most, if not all, mode of universal scaling. So there's an enormous amount of work to be done in checking this. And as I said, I'm not the one to do it. I have given the idea. Okay, let's go back. How do we validate these ideas, or if you don't believe they're ideas, conjectures? How do we validate them? Well, here is the argument, and I want to express the points of the argument. Human beings evolved into different societies, different cultures, different areas of the world. Influenced by the climate, and it is my claim, and not only mine, but my circle of friends who are architects, that indigenous architectures have evolved universal scaling. And not only in the monumental architecture, but in the vernacular architecture, in the houses, in the everyday habitations, in everything. If this is true, as we claim it is, then universal scaling is innate to human beings, not to a particular culture. If something is innate to human beings, then it's extremely important. Now, as I said, we have to discount the obvious exceptions, like the pyramids and military fortifications. The pyramids had to appear unapproachable because the body of the pharaoh lay in the middle, and you don't want anyone to disturb the body of the pharaoh. So the pyramid is a shape that psychologically tells you, keep away. It's not an inviting shape. Whether anyone in the audience wish to discuss the psychological impact of the pyramid, the glass pyramid in the Louvre, that's a good topic for discussion, but I'm not going to do it in this particular lecture. Nevertheless, I'm looking for innate reasons to apply universal scaling to architecture. Let's look at a major typology of the 20th century, the skyscraper. The one on the left is the skyscraper we build today. The one on the right is the representative of the early skyscrapers of the turn of the 20th century, late 19th, early 20th century, up into the 1920s, and that's about it. After 1920s, we had Ludwig Mies van der Rohe give the very simplistic minimalist design for the skyscrapers, and most skyscrapers adopted that with very few minor variations in recent years. I think that many people agree with me that the early skyscrapers have a certain charm. Now, for a large building with enormous amount of stories to possess a certain charm, that's quite an achievement. And I claim that the charm comes from the subdivisions, namely the universal scaling. You can see in the skyscrapers of Louis Sullivan and other early skyscrapers. Well, there is no scaling in the monolithic skyscraper because that's defined on a single scale. The vertical scale, say, even in the horizontal scale, when we look at the horizontal dimension, there could be some articulations, but those articulations are, say, another scale. So where the viewer looking at this from a distance and approaching the skyscraper expects 20 different scales to be evident, they see just two: the actual width of the skyscraper and some articulation. And minimalist skyscrapers even try to get rid of that second articulation, so there's nothing left. So this discussion uncovers something else. Not only not using the universal scaling, but a deliberate avoidance of the universal scaling for a certain aesthetic effect. Let's look at an application to house facades. Here are two houses, residences of approximately the same size and shape. They happen to be, the overall facade happens to be quite close to the golden rectangle, but that does not concern us here. What concerns us is the satisfaction of universal scaling. Well, the one on the left does not have universal scaling. It has one or two subdivisions, but that's it. The one on the right has subdivisions. It is an Art Deco building that has subdivisions. If we ask ourselves which of these two houses we like better, it's a very bad question, because that tells us preferences, aesthetic preferences, which are usually learned and have associations with how we grew up, what culture we are in. Nevertheless, the one on the right with the subdivisions, I think gives a better physiological response. What I just drew, in order to make the comparison between the two residences, was a shape seen only on the larger scales. But as I keep emphasizing throughout this lecture, it is on the smaller scales that the difference is really dramatic. In the modernist house, which was shown on the left, there are no smaller scales, and thus there is no scaling hierarchy. 1 or 2 terms, and that's it. So to see that, I have shown here the 2 buildings again, and I have magnified a piece of each building. And you see, I magnify a piece of the building on the left, and there's blank, there's nothing. I magnify a piece of the building on the right, and there is substructure, articulation. It is there. And I can keep magnifying until I get down to very, very small details. And we have substructure. Well, this is the essence of the universal scaling, that there is substructure all the way down in scales as you go. Now, at this point, I expect the following question to arise, and I have the answer ready. Yes, it is true that I have picked on the building on the right, I have picked a point where there is substructure. But there are also regions of the building on the right that it's quite smooth. There is no substructure. Well, the scaling hierarchy does not mean that everything is covered in detail. It means that there is a region or a few regions where detail gets focused. The articulation becomes more intense. You get smaller and smaller subdivisions. If you do it everywhere, then it becomes too much. And of course, some architectures do subdivision everywhere. Others have subdivisions in focal points, and the architect decides where to have more and more detail. And that's what I'm referring to. So this is not a dishonest choosing of a region that has particular detail. It is part of the universal scaling that there are regions, and those regions are carefully selected. Well, I can tell you now, where are those regions? Those regions are where the user will experience them to better effect. So you see, the detail I show is around the doorway. Well, this is the most frequently visited area of the building. If you have such detail close to the roof, it is less effective, and it probably will be wasted. Now, I wish to discuss another application of the universal scaling sequence, and that is the wide boundaries of an element. An articulation needs its edge defined. So in order for this to be commensurate with universal scaling, an edge or a center should have a lip, a thickening, a definable boundary. And I don't mean a line, I mean a thick boundary. So this concept, of course, will give us a wide door or window frames. It gives us baseboards, pilasters, all elements of traditional architecture all over the world. And those elements are precisely the ones that were removed when, at the turn of the 20th century, there was a movement to show off the strength of industrial materials. Namely, we don't need a beam over the door because we can create something out of very strong materials. So, the same thing for the window. We can have a sheer edge coming to the window. Well, people are building this way today without realizing that there was a psychological statement to having windows without frames and doors without frames. And I'm trying to get back to the positive response that one gets by using a door with a wide frame. Here's a nice medieval door, Western medieval door, where the frame is defined by elements, architectural elements, and it is so wide that we satisfy the universal scaling. Here, the window in the middle is rather minimalistic, but it acts as a frame of the other structure, so that we see the ratios of the larger length to the smaller length is consistent with our universal scaling. And the centering of this window gives a certain balance and symmetry. Incidentally, this is not a modernist window. This is from Islamic architecture, 14th century. There is a balance and a coherence to this because of such scaling, even though there is no more detail here. So a summary of what we have done before I go into something else totally new. I want to use the ratio of lengths to aid design and to introduce a change of thinking about proportion. Proportion has been identified as the ratio of the size of the rectangle. Well, that's not what I mean. Instead, I want to compare the dimensions of objects measured along the same direction. So these are the ratios of objects that I can measure along the same direction. So either vertical, horizontal, along the 3 dimensions actually. We have the 3 X, Y, and Z directions, and we can apply the universal scaling to all 3 directions. And there's nothing magical or mystical about this, as there is a cloud of mysticism associated with a golden section, and of course, as a scientist and mathematician, I don't buy any of that. And okay, to move on to something totally different, but which turns out to be essentially important. Biophilia. What is biophilia? Well, one of our greatest living biologists, Edward Wilson, has introduced a term to describe an innate connection between all living beings. And specifically, human beings have a biologically founded link to other life forms. This connection is genetic. It resides in the common parts of our DNA. Now, let's look at how the human body evolved. The human body evolved to respond to the natural geometries, which I have, not only we know to be fractal, the certain colors, the certain scaling, the universal scaling, there are symmetries. These are the natural forms. Well, over several million years, humans developed an extremely accurate sensory system. And how was this sensory system developed? Well, by evolutionary processes to help us to deal with the natural environment. So our system is fine-tuned to perceive positive aspects, food, friends, and mates, and also threats. Tiger is about to pounce on you, or other threats. So we have this tuning that, well, not only tuning, we have the entire development of the human sensory system that we use to experience architecture, and it is fine-tuned to certain natural geometries. The fine-tuning includes the detection of pathologies of our body, and that is also signaled by the departure from natural geometries. I can think of a host of things to say. Let's see, heartbeats. Heartbeats have a certain fractal structure. I'm not going to include that in the talk, but there was a pioneering study done by Bruce West showing that when a pathology of the heart sets in, the heartbeat changes its fractal structure in a way that it becomes non-fractal. Now, this is an extraordinary thing, and certainly the individual who is having heart problems notices the heart beating in a different way. They cannot analyze their heartbeat to see if the fractal structure is there or not. But doctors now can do this analysis. And here is a fractal structure in the temporal domain. I've been talking so far about fractal structure in the spatial domain. Plants, trees have a intrinsically fractal structure. So anyway, without getting off track here, our sensory systems are built to detect these geometries. So we require constant contact with this type of geometry, the geometry of biological structures. And if we are deprived of contact with this geometry, specific geometry, then we get ill, or we are predisposed to getting ill. Well, the experiments have been done that show that post-operative healing in hospital rooms that have positive biophilia are faster than post-operative healing in hospital rooms that have no biophilia. And this is a remarkable study done by Roger Ulrich about 20 years ago, and that has spurred a whole movement of investigation now being done in hospitals by doctors. Not so much by architects. Most architects don't know about these fundamentally important findings. So the basic experiments are the following. You just find in the same hospital exactly the same rooms, some of which look out into real trees through a window, and the others which have no windows or look out into a blank wall. And you just measure the conditions that patients recover after the same type of surgery, and then you compare, and you see a remarkable, a significant percentage improvement when you are able to look at a tree. Now, different studies done in Japan rather recently show a confirming effect, not in the time taken to heal, but in the amount of pain medication required. Patients that had patients that had a biophilic environment required less pain medication during their post-operative healing than those that had just a bland industrial hospital-like environment. Now, many hospitals in Europe are starting to utilize, or have already started to utilize, these findings by having very small but plentiful and easily accessible internal gardens. And in the rooms where patients are recovering who cannot move from the room, they're mimicking natural effects, either by bringing plants in or even a fairly detailed and realistic photo of a plant, which is not as good as a real plant because the real plants have other properties. But still, even with these substitute biophilic effects are still observable, and the light, the quality of the light, hospitals are starting to employ new light fixtures that give a more natural light that is broken up. So we are experiencing a rediscovery of things that people intrinsically knew that made them feel better. Being close to nature is more than an aesthetically positive experience. It is rejuvenating to your physiology. And there are studies that show conclusively that social and mental health deteriorates in natureless surroundings. Okay, so we required healthy environments for our health. We want a positive emotional response that reduces stress and raises resistance to disease. There are two things that are playing simultaneously here. The suppression of environmental factors that raise our distress, and a certain emotional regeneration, a positive feeling that comes from architecture. We know that we get some sort of emotional nourishment and regeneration inside a great building, or even a modest building that has special geometry, and these buildings are usually older historical buildings that have been found to have these properties, and there's nothing magical about this. This is the geometry of the building. This is the essence of a successful architectural conception realized in materials that gives us regenerative feelings. The great religions of the world, it was their aim to give this feeling to the worshipper. when the worshipper enters the house of God. You want to be regenerated. Well, can we create buildings today that give the same feeling of regeneration? And the answer is yes. There are architects today working in traditional typologies who use universal scaling intuitively. They have not learned it from me. They have developed it intuitively. They have learned it from the traditional typologies. But very few people can get this kind of training today. They have to develop it on their own. Now, by traditional architects, I mean traditional Shinto Japanese architects, traditional Chinese architects, traditional Islamic architecture in its many, many different varieties, traditional Indian architecture in India, northern India, southern India, and not necessarily Western classical. I am in contact with my friends who are classical architects, and I find that I have very little to teach them because their training, they have a memory of classical architectural typologies, and that's enough to guide them to instinctively use universal scaling today. Now, what I'm trying to get at is to work with design outside the traditional form language. So that's the problem today. Every architect wants to be innovative. They are reluctant to apply a traditional form language. So I would like to do the following two things. One is to validate each traditional form language that exists anywhere around the world to be used again today without having that architect condemned as being old-fashioned. I think it's a horrible thing and it is totally destructive. The second is to help architects who want to reach out and start a new form language for themselves. Well, this series of talks will give useful tools, I hope, that will help architects in reaching those goals. So my second main goal is to give tools for design outside the traditional form language, tools that will enable an architect of today to develop their own new form language.